All right, well, I've already created a database here. I've created a database called memdb. And that's because if I'm going to use memory optimized tables, there is something I have to do when I create the database. I have to create this thing called a file group that contains memory optimized data. So don't worry about the details of that too much. It's just something we have to do when we're going to be using this technology. We have to add this type of file group to the database. But I've already done that, and I'm now ready to go and create a memory optimized table. So way back at the beginning of this course, we looked at creating tables using the create table statement, and that's exactly what we're going to do. We're going to use this memdb database. We're going to create a table called dbo.memory table. It's going to have an ID column which is of type integer, which is the primary key. And because it's an in-memory table, I've got this option of using what's called a non-clustered hash, where I basically just hash the value into in-memory buckets. So I'm storing it in locations in memory based on the value that's in that column. So I'm storing that data in memory. And I'm going to have a date value, which is just a date time, and that's going to allow null values. So we're creating a date time, a column called date value, which stores date time values. Now the important bit here is in this with clause, I've said with memory optimized equals on. So it's an in-memory table that I'm creating. And the durability is I'm going to persist the schema and the data to disk. So as well as having the data in memory, it's going to be persisted so that when the database is taken down and then brought back up again, the table still exists. Sometimes you might just want to store the schema. You might want to let the data get deleted every time the database is taken off, maybe just because you're using it as some sort of cache for a web application or something like that. But we're going to go ahead and create that table. Let's go and do that. And just for comparison, I'm going to create the same table, the same structure, but just as a regular on-disk table, the same type of table we've been using all the way through. So we're just going to get a table called disk table, which has an integer ID column and a date time, date value column. So exactly the same structure. Let's go ahead and create that. And what I'm going to do is I'm going to use a transaction. We talked about transactions earlier. We're going to use a transaction and we're going to insert 500,000 rows into the disk table. And while that's running, I'm also going to insert 500,000 rows into the in-memory table. So I'm using pretty much exactly the same code, except for the name of the table. So I'm just going to copy the code for the memory table to the clipboard. And I'm going to go and run this code that inserts 500,000 rows into the disk table. So let's go and run that. And off that goes and starts running. I can see it's executing query, and I can see down here the amount of time that's elapsing as that goes along. So we're at 6 seconds now. And while that's running, I'm just going to create a new query. And I'm going to paste in the same code and insert into the in-memory table. So we'll run that at the same time, simultaneously. We're running both of these queries. So this one starts executing, and I can see the amount of time elapsed down here. And that one's now finished. So that took 7 seconds. And if I go back to this one, well, that's finished as well, but it took 17 seconds. So I can already see, because my memory table is in memory, using a transaction to insert 500,000 rows was quicker. It was 10 seconds quicker doing that in the in-memory table than on the disk table. And just to verify that we have in fact done that, if I select the count of rows from the disk table, there's 500,000. And if I select the count of rows from the memory table, there's also 500,000. So no cheating, we've got nothing up my sleeves. We're just genuinely seeing that it's faster to insert data into an in-memory table. Now if I go and delete from the disk table, let's go ahead and do that. We'll delete from there. Off it goes, and it starts deleting. It's taking a little bit of time. Again, we'll just do the same thing in another connection from the memory table. So we'll just go and delete from there. And that happens almost instantaneously. It was 0 seconds on the clock for deleting from the in-memory table, whereas it took 14 seconds to delete those rows from the disk table. So again, the delete is another thing that's taking longer to do on the disk-based table. Now, one of the things we talked about when we were talking about this earlier on was we looked at the idea of native stored procedures. So as well as creating these in-memory tables that are actually C# structs that are then compiled to DLLs, we can create stored procedures that are C# code compiled to DLL. And I'm going to create one called insert data. And the way that we make it a native compiled stored procedure is we say with native compilation. So native compilation, another couple of options on here we don't need to worry too much about. And it's going to use this atomic transaction. It begins a transaction, and it's going to do the same thing we did earlier on. It's going to loop around. It's going to insert 500,000 rows into that table. So we'll go ahead and create that stored procedure. So I now have a natively compiled stored procedure that's an in-memory DLL and a natively or a memory optimized table that again is an in-memory DLL. So let's run that stored procedure, which does exactly the same insert we did earlier on. And you might remember it took 17 seconds to insert 500,000 rows into the disk-based table. It took 7 seconds to insert 500,000 rows into the memory table. If I use a memory optimized stored procedure, well, it took less than a second to insert 500,000 rows. So again, we're seeing that in-memory technology for both tables and stored procedures, in this particular case, because it's a latch-bound workload, there's a transaction going on that's locking pages, it's significantly faster using this in-memory technology to work with these tables. All right, so we've covered a few things in this module to optimize performance. Let's just recap on what we've looked at. So we talked about using indexes to optimize select performance, and you can have one clustered index on each table and multiple non-clustered indexes per table. It does optimize the select performance. You do have to be careful that, if you have just index everything, then your inserts and updates are all going to suffer performance issues, but it's a good way of optimizing select performance. We talked about column store indexes. Those work really well in those kind of large-scale data warehousing type scenarios. And what we're doing there is effectively indexing based on columns rather than rows, and we're storing those column indexes in memory. So we're getting some good performance optimization from that. Works very well when you've got highly compressible data, columns that have the same repeated value in them.
And we saw that there were some improvements in SQL 2016 for this.
Yeah. And we've also talked about memory optimized tables. So the idea of creating a table, but actually when we create it, under the covers, SQL Server generates a C# struct that represents that table, compiles that into a DLL and stores that in memory. So we get that in-memory performance. And we can do the same thing with stored procedures, with natively compiled stored procedures. The big scenario where you want to use that is where you have contention-bound workloads, where you've got multiple people trying to access the same data at the same time. If you're using transactions to lock the tables, then that can give you contention issues. In-memory tables are a great way of optimizing that particular workload. So hopefully you've enjoyed looking at ways of optimizing the database. Join us in the next module as we move on through the course.